All right, we're going to look at a funny little problem here that combines aspects of, well, gravitation and oscillations, and that is that if you were to dig a tunnel completely through the dead center of the Earth from one side to the other, and then right when you start your stopwatch, somebody at the top decides to just go full send and down into the tube. Right, so we're going to look at how they'll move. Right, of course, when they jump in, you're going to have the force of gravity on them, pulling them down toward the center. So there's the force due to gravity. Now, as you might imagine, when you get to the dead center, you'd have mass all around you, pulling you in all directions. So the net gravitational force will be 0 when you're in the dead center. Okay. As you approach the center, what will happen is this gravitational attraction is going to decrease and decrease and decrease, right? Because it's dead, it's 0 once you get to the center. So here it's going to be smaller. So I'll write the F grav there. Now, by the time you get to the center, you'll be going so fast that, yeah, there will be no force on you, but you'll overshoot the middle because you'll be going at high speed and start heading out this way. So once the person is here, that gravitational force would be flipped around backwards like this, but yet they're still going quite fast. And assuming we'll do the usual thing and make it a little bit artificial by leaving air drag out and things like that. And by the time the person comes out on the other side, where they'll kind of run out of speed, the force will be, well, as large as it was here, but just in the opposite direction. So there's your F grav going back. All right. So before we even start with this, it almost seems like you've got motion that's kind of like if you had like a stretched spring, because when you're far from the center, you have a big force that gets you to go toward the center, and the person falls down toward the center, is going at high speed. Well, then you can think of it as almost like the spring starts to stretch over here and pulls them back. So you'll get this funny back and forth motion or oscillation. Well, let's just see how that plays out, and as you'll see, it actually does end up being incredibly similar to a spring. As usual, when you want to learn how things are going to move, you start with F equals ma. So we'll say the sum of the forces on the person is their mass times their acceleration. And so the only force on the person is the gravitational force, right? So that force, the sum of the forces, it's just going to be F grav. Right? And your gravitational force goes like this, minus big G times the two masses. Mass of the Earth, or no, mass, well, actually we got to talk about this for a second. Divided by distance squared. What we need to talk about a little bit is when the person is at the surface, the mass that's relevant for GMM over R squared is actually the entire Earth. Now, when the person gets to this intermediate location, let's say, the mass that's actually relevant besides their mass is the mass that's just enclosed within the radius where they are. So I'm going to write MENC there, right? And so at any given moment, the mass that's actually attracting them toward the center is the mass that's just within their location, okay? It turns out if you're in this intermediate location here, the net effect of all the mass that's kind of in the outer ring here, that ends up being no net attraction to the middle. So you do just end up getting attraction from the mass that's enclosed. So we kind of need to do a little side problem to figure out how much mass is actually inside of here. Well, if we treat the Earth as like uniform, what we can do is we can say the mass, so we're going to do a little side project here to just get the mass that's enclosed. One way to see that is you can just think of what fraction of the Earth is this ball compared to the whole thing. So you could say that's like volume enclosed over the volume of the entire Earth. I'll say total. Over or times the mass total of the Earth. Okay, so E for Earth. I guess I'll go VE for Earth. V enclosed over V of the whole Earth. Well, so just to see how this plays out, the volume enclosed is going to be volume of a sphere, 4/3 pi r cubed, divided by 4/3 pi radius of the Earth cubed, times the mass of the Earth. So a lot of cancellations here. The 4/3 pi's are gone. So it's really just the ratio of the ratio of the cubes of the radius times the mass of the Earth. And so what we can do is substitute that in there. Okay. So over finally, kind of going back to the top end, we'll have like ma, the person's mass times a, equals minus g. And then instead of mass enclosed, we're going to put this this expression. Minus g, we have r cubed over radius of the Earth cubed times the mass of the Earth. So that's the mass enclosed, times the person's mass divided by r squared. All right. So what we can do with this, you can see there's quite a few little a couple cancellations. One, of course, is that the mass of the person cancels out. So it doesn't matter whether you throw a ball in there or whether a person dives in there or you drive a Toyota Camry down there. It's gonna move the same. So the mass cancels out. And so let's just get this set up. So you have the acceleration, which is actually d squared r by dr by dt squared. Right, second derivative of position is the acceleration. So I'm just going to put that in there now. Equals. Now let's deal with all these constants. You have minus g, mass of the Earth, over radius of the Earth cubed, times, now r cubed and r squared will conspire to make r. Right. So what you have right now is this equation of motion. Right. That the acceleration is proportional to how far you're pulled out away from the center, and the acceleration is back toward the center, right? So where you've seen something like this before, whether you realize it or not, is if you look at a mass on a spring, when you do F equals ma with a mass on a spring, the force, which is ma for a mass on a spring, is minus kx. And what happens is if you divide the mass under, so you get a equals minus k over mx, and you get this equation of motion for the spring. That's d squared x by dt squared, because that's the acceleration, equals minus k over m, times x. Right? Well, a couple things that you might already know from a mass on a spring, if we just kind of stay in this, thinking about this for a second, is the period of motion is 2 pi root m over k, or the reciprocal of this coefficient. Okay, so that's from studies of mass on a spring. Well, what you notice is these are the same equations, just with different critters. Okay, so you have second derivative position with respect to time is minus a constant times position. So these are physically exactly alike, right? And so what that means is then derived quantities of that should be, well, essentially exactly alike. If the period here is 2 pi square root of the reciprocal of this thing, what that means is this is also going to undergo oscillations like a mass on a spring, but the period is then going to be 2 pi times the square root of reciprocal of this mass, r the Earth cubed over gme. Right? So the upshot is this person is going to move almost as though they're hooked to a spring, boing, 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 back and forth. And this is the period that they would have moving back and forth. Well, a couple things that you could plug in. So it turns out the radius of the Earth is about, it's like 6.37 times 10 to the 6th meters. Big G is 6.67 times 10 to minus 11. What is it? Newtons meters squared per kilogram squared. That's like the gravitation constant, Newton's constant. And then, let me make sure I didn't mess this up. Yeah, this is right. And then the mass of the Earth, it's like 5.97 times 10 to the 24th kilos. Right? So those are constants that you could put in here. And it turns out that if you do shove those in, I encourage you to try it. If you plug it in like this, you'll get the period in seconds. If you change it to minutes, you'll get around 84 minutes to go back and forth. Okay, you'll have to convert from seconds to minutes. So you jump in here at the North Pole. 42 minutes later, your head will pop out here by the penguins at the South Pole, and then back you go. And then 42 minutes later than that, for a round trip of 84 minutes, you'll go back and forth between the North Pole and the South Pole. So that's this tunnel through the Earth problem. The main points here, two big keys. First of all, it's that this gravitational force only depends on the mass that's inside of wherever you are. The mass that's inside, you can just think of it, if we treat the Earth as being uniform, it's just the ratio of the volumes times the total mass, right? So that's where that came from. After playing around with that, even though this gravitation force goes like 1 over r squared in general, but the mass enclosed goes like r cubed. And so that's why this force ended up being linear in r as you move out, so it's just like a spring. And so you get this equation of motion that's exactly like the spring, and that's why the period, which is 2 pi square root of the reciprocal of this coefficient of the position, same thing here. The period is going to be 2 pi square root of the reciprocal of the coefficient of the position here. So that's the tunnel through the Earth problem. Bounce back and forth.